Hi, students. Mr. Halpern here. This will be the second video for heat of combustion using a calorimeter. So in the first video, we talked a little bit about what a calorimeter is and how we would set it up. Um, if we ask you guys to actually build a calorimeter, and actually you could do this at home. It's very simple. You take a can or some sort of container that has relatively sealed top, except for an area where you can put a thermometer. You can put a thermometer in there, like a thermometer you use in your take your temperature, and then you would have like a candle or something that you want to burn that you could measure the heat of, and you could do this. One of the interesting things is that if you do that measurement, you're going to burn a certain amount of that candle, let's say, or in this case, the Human Torch's hand. And depending on how much you burn is going to give you more energy. Well, that doesn't really tell us a whole lot about the substance. What we want to do is try to figure out a normalized way of describing, hey, this is a really good energy source and it has a lot of energy, because we have to sort of compare apples to apples. So one way of doing that is doing something called the heat of combustion, which is the title of the top of the notes here. And this is a little bit different than just measuring the heat of the reaction or the heat released. It's incorporating not just the energy, but it's per gram. So you're dividing it by the grams. All right, so it's not really that much of a layer, but I'm going to just go through this really quickly. So as we've done in previous problems, right, Q, M, C, delta T, we have a mass. In this case, it's the mass of water. Now, it's really important that we continue to use the mass of water. Now, 500 is our mass. We know that water has a specific heat of 4.18. Probably don't have to even see that in the problem anymore because you know that. And the change of temperature. The temperature rise is 1.4 degrees Celsius. All right, so we're going to get an answer here. This is 500 times 4.18 times 1.4. And I get 2,926. This is joules. Now, I have to convert this into kilojoules per gram of our burned material. You might have been asking, all right, we used all these numbers. What about this number, right? And this is where this is going to come in. So we have to have a way of converting this. So the first thing you have to do is convert this number of joules into kilojoules. How do we do that? We take their decimal place and move it over 1, 2, 3 times. We have 2.926, so let's call it 2.93 kilojoules. Okay, now that's how much we burn for 1.946 grams of the Human Torch's hand. Right, that's how much energy we were giving off for that amount. But what if we wanted to say, let's compare Human Torch's hand to a candle or to gasoline? What we have to do is use a same amount that's burned and then compare the amount of energy. And that same amount we typically say is the grams. So grams used would be, dividing it would be 0.1946. And so I take this number and divide by 0.1946, and I get 15 kilojoules per gram. So for every gram that the Human Torch's hand burns, right, 15 kilojoules of energy comes out. And that's a number that we can compare to other fuels. Let's take a look at another example. Let's say that 0.3423 grams of a pentane, C5H12, was burned in a calorimeter. The temperature of the calorimeter and the 1,000 grams of water contained therein rose from 20.22 to 22.82 degrees Celsius. And again, the heat capacity of water is 4.18. So the first thing is, how many joules? Well, we have to do Q is equal to mc delta T. Next, we have to say, all right, we have 1,000 grams of water. Specific heat is 4.18. And delta T is, let's see, do this quick mental math, 2.6 degrees Celsius. Okay, the last step is just multiplying all this through. And I get 10,868. All right, now that's in joules. So that's my answer for the first part. The next part is, what is the heat of combustion? Heat of combustion, remember, is the kilojoules per gram. So I have to go from joules, which I have here, to kilojoules, and then I have to divide by the amount of grams that were burned. So I take my 10,868, okay, joules, and I divide it by 1,000, or again, I move the decimal place over 3 times, and then I divide that by the number of grams, which is 0.3423 grams of pentane. All right, and what do I get? I take that, I divide it by that, and I get 31 point, call it 7 kilojoules per gram. Oops. All right. So now we're rocking and rolling. Now we can say a lot of things. Well, we can say, hey, Human Torch's hand, that's not that much energy, right? Compared to pentane, it's only about half of the amount of energy that was given off per gram. So, I'd rather use pentane as a source of energy. Last but not least, we have molar heat of combustion. This is an extra layer from heat to heat of combustion to molar heat of combustion. So the molar of heat of combustion is the kilojoules per mole, and we have to know what the molar mass is of pentane. Well, let's think about this for a second. First, we have to figure out what is the molar mass of pentane. So pentane is C5H12. How do we figure out molar mass? Well, hydrocarbons are pretty easy. It's just carbon and hydrogen. So we know that carbon is 12 grams per mole and hydrogen is 1 gram per mole. So if I have 5 of them, 5 of the carbons, it would be 5 times 12. And I add that to 5 times 1 gram. And I get a total of 75 grams per mole. Okay, so this is my molar mass. Now, it's not my molar heat of combustion. And what I have to do is now convert this into a molar heat of combustion. And the way that I do that is by taking my amount of grams and multiplying it by the heat of combustion. Why do I do that? Let's take a look. Well, if I have 31.7 kilojoules per gram, right, and a mole of pentane is 75 grams, then the molar heat of combustion would be the amount of energy given off for that many grams in a mole, 75. So I have to take 31.7, multiply it by 75, and I get 2,381.2. This is kilojoules per mole. Now this is a really good answer here, right? It's not an easy question to go to the molar heat of combustion. Now, when I look at propentane right here, I notice that my number of molar heat of combustion, if I look at it, is much different than the measured heat of combustion, the molar heat of combustion. Why is that? The reason why you have a lower molar heat of combustion compared to the number in the textbook is again because you're doing an experiment. And when we do experiments, we have a lot of places for error. And one of the places for error, as we talked about, is the design of the calorimeter itself. When we do this, we assume again that all of the energy from a fuel goes up into the container holding water, when in fact you have a lot of energy being lost out here. Right? You also have a lot of energy being lost in heating up the container itself. That's why we don't want to heat up or touch a container like a hot pan, right? A skillet that's been really heated up, right? We assume that there's some energy, going directly into the pan. That's why we have to wait a few minutes when we're, cooking on a stove top to heat up the pan first, right? So that's it. That's why you have a slightly lower number of molar heat of combustion there, and also why you have a lower heat of combustion as well. All right, take care. That's it.